And there we go. We were looking at thin lenses last time. And this is what our last lab is going to be next week. Is making images with these with lenses. How transmitted light is refracted and focused, bent and such. And of course, that's fundamentally the difference between reflection and lenses, is that with a mirror, the light of interest at least, is the light that comes out, that reflects back towards where it came from. With lenses, the light of interest is the light that transmits through and comes out the other side. Other than that, what we're actually going to see is that the equations that we use to calculate the focal length and images and the rest of the image distance and the object distance, the equations you're going to recognize real quicker. They look exactly the same. Hopefully we'll end this lecture today on the thin lens equation. The lens maker's equation, I think is what they call it. So, a little recap. Who can tell me why we call them thin lenses? What is the distinction we make when we say a thin lens as opposed to a thick lens? Talking about the Fresnel lens? No. Yeah, the Fresnel lens that's sort of like the ultimate thin lens. That's thin lens with anorexia. Okay. But no, that's yeah, lenses, your glasses and cameras and other things, telescopes, they are all spherical. Then you're not going to, unless you spend a whole big old honking pile of cash, you're not going to get a lens ground to a parabolic curvature. They're going to be ground to a spherical curvature because it's easy to do. Matter of fact, if you ever built your own telescope, that was probably the bulk of the work you did, was you hand ground a lens and then polished it. Hey! Yay, y'all aren't by yourselves. Don't forget to sign in. The criteria for a thin lens, and yeah, but basically it does mean that the lens is thin relative to its diameter. But the criteria that makes that so is the same criteria that addresses the issue of spherical aberration. And that is that as long as the diameter of the lens is much, much smaller than the radius of curvature of the surface, then it's a thin lens. That means it's going to be thin in the middle compared to its diameter. And yeah, even those glasses on those kids that y'all used to make fun of in grade school that you called the Coke bottle glasses, those are still thin lenses. And y'all were mean to make fun of them, by the way. No, actually, no. Yeah, they use mirrors and reflectors. That's not. Yeah, normal. They do put lenses in, and they definitely put lenses in the Hubble because they had to go back and put in contact lenses to fix it. Contact lenses? Y'all don't remember that happened? Oh man, that was. Oh, everyone was. It was all over the news. Pass that around. Make sure everybody gets signed in. They spent billions of dollars building the Hubble telescope. They launched it in the shuttles. They got it all up there, and they got it all put together, and then they turned it on, and they looked at this galaxy that they were finally going to get to see this big, sharp, clear, high-resolution image, and it was like a blob. It was like one of those, you ever seen pictures that people take of Sasquatch? Notice how they always come out looking like blob squatches? Well, that's what they got. They got this big, fuzzy blob where a pristine, high-resolution image of a galaxy was supposed to be. And all of the people on the team, from the highest administrators all the way down to the lowly technicians, every last one of them just soiled their pants in the middle of the night when that news broke. They went back the next day to NASA thinking that they were all going to be unemployed. Instead, they set about figuring out, okay, how do we fix this? Yeah, they came up with a fix where they went in and they put in corrective lenses inside the Hubble to realign the problem was that a mirror was ground imperfectly, and so they fixed it, and we got some really great high resolution images. Now we're not really going to look into thick lenses. Normally, when you start getting into thick lenses, you're starting to get into things like prisms and compound optics, where it's not just about bringing you the light to a focal point, but you're actually extending that focal point, and you want more offset. And really, that's because going to a thick lens is just the opposite of doing a Fresnel. It's saying you don't just want it brought. You don't just want it brought down, bent to a new angle. You want it offset and then going out the other side at a different angle. So, when they start doing compound lenses and some of these big, expensive camera lenses, I used to have one actually. 600 millimeter telephoto lens, about that long, that big around at the objective lens. Oh, that was about a $4,000 lens back in the 80s. I wouldn't even begin to think about pricing one today. But, don't get me wrong, you could buy 600 millimeter lenses for $100 or less. But this one had a column of highly polished and ground precision optics that were, that were not all convex focusing lenses. They were a combination of converging and diverging lenses to correct for chromatic and spherical aberrations, and that's another issue that, frankly, I don't think we're going to cover in this chapter. But there's called chromatic aberrations that happen not because of the shape of the lens, but because of the wavelength of the light. We talk about the index of refraction like it's one number, but the index of refraction actually varies based on wavelength. And if we were going to do this as instead of as geometric ray tracing, but if we were doing this as a wave problem, then we would run into that. Look at that chart behind you. That's how it's produced. White light is shined through a lens or a prism, and it is bent, but the wavelength of the light depends on how much it's bent. So that it looks like white light going in gets smeared out into this spectrum of color coming out the other side. Because each wavelength has its own unique index of refraction. Anyway, we're not going to be looking into that much detail. But we're going to stick to geometric ray tracing. But I will tell you this. Each of you will need a small ruler of some kind for one of the homework problems, because they have you do ray tracing to come up with, to actually, to find out what the image distance of an issue of a problem they set up. They give you the object distance, tell you to do the ray tracing, and then you find the image distance. And they want you to find it graphically first by actually doing the ray tracing. And so I'm going to start today by showing you how that works. Anyway, in order to do the homework problem, you're going to need to actually measure how many millimeters over do you put this, and then draw the lines. You need to be able to draw perpendicular lines with a protractor and stuff. So, if any of you don't have that stuff at home to do that with, I gotta believe you've all got a little ruler, and if you need to, a protractor. You really can probably eyeball the lines perpendicular close enough to do the problem. But if you don't have it, you need to, come by my office. You can borrow some from here, and you can do that problem in my outer office. All right, ray tracing. We're looking at lenses, which means we're now looking at light that is not reflected, but light that passes through. It's transmitted. And it comes out and it transmits to a focal point where you can burn the ants. Or your hand if you hold it there long enough. Yeah. You can start a fire. You can light a cigarette with one of these. I can promise you that. Oh yeah. Of course, what do we know about this focal point? It's the most concentrated point. Thank you. It is not perfectly concentrated because of, somebody say it out loud. Those all have an impact, but not this much. Yeah, no.
Water density.
Actually, air resistance does play a part in light transmission because the index of refraction in air is not quite the index equal to the index of refraction of vacuum. No, but the index of refraction in space would be exactly 1 as opposed to 1.00003, I think. Now, if I squiggle it enough, you can't tell that I don't know how to spell it. Spherical aberration. I think this second B should be an H. I don't know. I don't look it up. Ask Google. Google knows how to spell it. Close enough. Thank you. Thank you, Siri. Because this surface is ground to a sphere, a spherical surface, not a parabolic surface. These rays are not going to pass through exactly the same point. There's a
like this one.
How Skynet starts.
It's how Skynet starts. You know, it clicked the "I'm not a robot" thing.
I love it. I am not a robot.
They gave me access to a $38,000 robot. This is what happened.
How Skynet
How many of you have ever seen the most useless machine ever built?
I've seen quite a few very useful.
There's two.
Quick switches off.
That's it. You flip the switch on and the hand comes out and pushes the switch back off. Yeah. There's the other one I call the Cajun wind-up toy.
Sounds like it's weapon mass, like mass destruction or something. A weapon? Cajun wind-up toy.
The Cajun wind-up toy. You've never seen the Cajun wind-up? Well, there's two versions. The one I'm thinking of, the machine version, is the block of wood with T-slots, perpendicular T-slots cut in it, and then two T ribs that pass back and forth through them with a hand on it that you crank it and they slide back and forth. Yeah, but it's just that's it. And if you're stupid enough, it'll keep you entertained for hours. Then there's the other wind-up toy, the Cajun wind-up toy. Tell me if you've seen it. Are you ready? All right. Enough jocularity. Focal.
Totally could use that on drunk people at the bar. I work at a bar.
Oh.
I'm totally going to use that on drunk people at the bar.
Okay, because of spherical aberration, these rays do not come to exactly the same point. This is why it is important to keep the distinction of a thin lens. The criteria for a thin lens is that the radius of curvature of the surface is much, much greater than the diameter of the lens. And that means that the spherical aberration is going to be very, very tiny. So it will become, even though you won't get a perfectly focused point, you will get the most concentration of light right there. And frankly, the reason they don't have machines to grind parabolic lenses is because this is smaller than you can see. Okay, so you see the image, it's still going. We'll see it next week in lab. You're going to make some images on paper and stuff with lenses. And
Is there more efficient versus less efficient? Like if the radius is like smaller to the size of the lens or bigger with a small lens, like small diameter of the lens, or does it change efficiency?
no, it just changes the focal point. What does it change when you change the focal point? The focal length. It changes the focal length, but what is getting ahead of ourselves here? But this is what the opticians and ophthalmologists, when they write a lens prescription, they specify it in diopters. You know what a diopter is? It is the unit of power. The power of a lens is simply reciprocal of its focal length. So diopter is the unit that is equal to inverse meters. 1 diopter is 1 over meters. Now, if these rays come in at a different angle, and I'm going to change colors of ink so you can tell what I'm doing, because this is probably going to get sloppy. But if these rays come in at a different angle, they still get focused. But to a higher point. That is what is called the focal plane of the lens. So you don't, in order to form an image, you've looked at the picture taken with a camera. You don't get just an image from right there in the center and then it gets all fuzzy on the outside. You get a nice flat picture of it, everything off to one side or the other. is in focus. Now, because of spherical aberration, if you make it far enough, if you make that image wide enough, then yeah, you're going to get out somewhere. You're going to start getting fuzzy images around the edges and stuff. Same thing would happen if you went to a non-thin lens. Even before you get to a thick lens, you're going to start getting all manner of aberrations out around the fringes. Somebody, give me the best known, the first example of that very phenomenon that you can think of. Yeah, no. No. Wide angle or fisheye lenses. Anyway. Say again? Yeah. Peepholes. All right. Let's talk about ray tracing. With thin lenses, as with mirrors, what is the focal length? Half the radius of curvature. Now, we're not going to go through and do a bunch of calculations of the angle of incidence and the angle of the refraction and coming out the other side. We're not going to do that analysis. We're just going to pretend like this lens, this thin lens, acts as a one change in angle at the center of the lens. So instead of trying to draw the curves and trace the rays through the refractive surfaces and stuff. But if this were the lens, it would look like this. Or that is a convergent lens. Because if it's convex, it's convergent. If it's concave, it's divergent. Where rays coming in here would diverge. So they would look like they were coming back to a focal point on the front side of the lens. No. This, you're really not going to run into this unless you start getting into optical columns, where you put, where you're designing something for a very precise and specific purpose, where you put in a column of lenses that you have it converging and diverging as you bring everything. You're correcting for chromatic aberrations, you're correcting for spherical aberrations, you're correcting for all the, any number of other issues that come up. We're not even going to start to talk about. If you were building that kind of a complex optical system, then you would run into this, where this would become a thing, where your image is actually over here, because the next lens in the column is going to have that image as its object distance. The image of one lens is the object of the next lens. And so, in that case, this would become a thing. And it's a technique that you would use if you needed to put like 1,000 millimeters of focal length down into just a few. Kind of, yeah. Here you draw your axis right through the center of the lens, normal to both surfaces. You put your object at some point. Now, you've got your radius of curvature, so you've got your focal distance right here. Here's your object distance. You want to find your image distance. Well, the focal distance on this side is equal to the focal distance on that side. I'm not going to bother going through to prove this to you, but I will tell you that that is true for every lens. It doesn't matter if they're convex, it doesn't matter if they're concave, it doesn't matter if they're different radiuses on different sides. If the focal length on one side will always equal the focal length on the other side. Just take my word for it. Okay. So, first thing, and then let me try to do this a little better here. There, focal length. Close enough. First ray you're going to draw is from the point on the object parallel to the axis to the lens, and it is then going to go through that focal point. The next thing you're going to do is draw one through this, from that same point on the object through this focal point, and it will emerge parallel. And at that point, you have your image distance. But just to be complete, pass a third line right through the center of the lens, and it should come right through that same focal point, that same image point. That will give you the corresponding same point of the image. And you'll notice it's upside down. This is what you're going to have to do on that one homework problem I was telling you about. Oh, look at this. Now, we did go through and derive the whole ratio of the distance, the reciprocal of the distance. The sum of the reciprocal of the distances is equal to the reciprocal of the focal length. I'm not going to go through and derive the same equations again, because they are the same equations. What you're going to find is that 1 over f is equal to 1 over d sub I plus 1 over d sub O. And it doesn't really matter what order you add them in. Addition is commutative. Put them in whichever order is convenient for how you're planning to solve the problem. This is called the thin lens equation. Oh, look here, 23.9, they get into combining lenses. And in 23.10, they go and work out the lens maker's equation. What do you think is the heart of the lens maker's equation? They change that to D or P. Power or diopter. Yeah. 1 over the focal length is the power of the lens. If the radius of curvature is 0.02 meters, what's 1 over 0.02? 5? It's something like that. If it's 0.2, and then the reciprocal of that is 5. So if it's a 5 power lens, that means it's a 20 minute. What's the reciprocal? 50? Okay, yeah, if you get a 50 power lens, that means it's got a 20 millimeter radius of curvature. That's a pretty short radius of curvature. That's not going to be a thin lens. But if it's 0.2, then it would be 5 power. So when you go to Walmart and you walk up to the reading glass column where they sell the reading glasses cheap, and it says this is a 1.5 power lens, that means it has a 1 over 1.5 meters radius of curvature. 2 power would be what? 0.5, 500 millimeter radius of curvature. Well, it doesn't really matter. That's the point is that the power of the lens is just the reciprocal of the focal length. So if they tell you the power of the lenses, just divide that into 1 and that'll give you the curvature of the lens. Now, we are going to run into some sign conventions that we need to talk about. The focal length is positive for converging lenses, and it's negative for diverging lenses. Focal length for converging lenses is positive. Focal length for diverging lenses is negative. So if they give you a problem and you have to do the algebra and find the focal length and you get a negative number, what does that tell you? That's a divergent lens. The object distance is positive if the object is on the side of the lens from which the light is coming. And this is always the case for real objects. But when lenses are used in combination, it might not be. And when you in this later chapter, when I told you here, you've got a virtual image, becomes a anyway. If the object is on the other side of the lens from where the light is coming, then it is a negative object distance. And the image distance is just the opposite. The image distance is positive if it's on the side of the lens that the light is transmitted to. If it's on the opposite side of the lens from the light source. And it is negative if it's on the same side of the lens. Here we're assuming that, and because this is ray tracing, remember, you can do it either direction and you get the same result. This could be the object, and that would be the image, or vice versa. But DO is positive when object, I'm not going to write all that out. You couldn't read it if I did. When the object is on the same side of the lens as the light source. The image is positive when it's on the opposite side of the lens from the light source. In other words, it's positive when it's exactly as you think it would be. When the object is here, that's the positive the object distance. The light is going this way. Then finally, there's the height of the image. It is positive if the image is upright and negative if the image is inverted. And H sub O, the object height, is always considered to be the positive case, the upright case. So if you put this as your object, then it's assumed that the object is a arrow pointing down, and that's the upright case. Okay? And so the inverted image would be an arrow pointing up. What determines if it's real or virtual? Object distance, not the image distance. The object is always assumed to be the positive image, the positive height, meaning it will be assumed that the object is upright, and therefore it will be treated as positive height. This is just standard, the standard that's adopted in all the textbooks and stuff. Well, no, you would see an inverted image if the image is negative. If the image height is negative, then it's an inverted image. If the image height is positive, then it's an upright image. Okay? And that's relative to a positive object height, not distance. Image distance tells you whether it's real or virtual. If it's positive, it's a real image. If it's negative, it's a virtual image. This is the image point. This is the side that the light comes from. So for an image, this is a negative image distance. It would be positive image distance if it were over here on the side of the transmitted light. Because it's a negative image distance, that tells you it is a virtual image, not a real image. And it's a real image is one that you could put a piece of paper there and you would see the picture on the paper, or the glass, or the film, or the camera sensor, or whatever. And as with the mirrors, the magnification is the ratio of the heights. Say again? A positive image distance, d sub I, is a real image. A negative image distance means it's a virtual image. The height, the sign of the height of the image will tell you if it's upright or vertical or inverted. The sign of the image distance tells you whether it's real or positive. Okay. Any more questions? Anything you want me to go back and cover some more or explain better? Maybe try to draw a prettier picture. Yeah, on that homework assignment, you really should be able to just kind of eyeball a perpendicular and get it close enough. I don't think you'll need a protractor to do that. But you will want to use a ruler with the little millimeter markings to scale everything correctly so you can get a... When I worked the problem, my answer for it was the image distance is a little less than 500 millimeters. Okay, so that's as close as you're going to get at trying to do this stuff graphically. That's why we learn math, because you don't have to do it graphically. You can just add the numbers and subtract them and do the arithmetic, and it'll tell you exactly within tolerance. Any more? Anyone have any questions from the homework? Have y'all started the homework yet? Okay, well, that makes it easy on me. Say again? Yes. Homework is due Monday. Next week is effectively the last week because we've got one more week after for final exams and grading and stuff. But next, say what? What? No, it's the final exam. It's not a final exam. It just means the last one. No, I'm not doing a comprehensive final. Everybody can stop sweating that one. Well, believe it or not, my objective has not been to fail you. All right, well, if there are no questions, then I will see y'all on Monday. Have a good weekend, and you know where my office is if you need help with anything.